Hi, welcome back to chemistry. Hope you guys had a nice Easter weekend and enjoyed having a nice long break. We were just diving right back into it. So last week we were talking about acids and bases, and we learned about the definition of acids and bases and how we can tell them apart, and also a little bit of the chemistry behind it, which is still pretty confusing, which is why we ended up with 3 different acid-base theories. Today we're going to talk more about how we compare them. You know, what's a strong acid versus a weak acid, or a strong base versus a weak base? Is there some sort of scale we can put them on? And of course there is. This is 6.5, the pH. pH is a measure of the acidity of the solution. And this has to do with how many H plus ions are being released into water when the acid is mixed with water. We already talked about that a lot when we were talking about our theories of acids and bases. Most of them rely on the release of H plus ions. H plus ions are hydrogen ions, of course. And so the more hydrogen ions that are released, the stronger the acid. Is basically what it comes down to. And we can actually put this on a scale from 0 to 14. This is called the pH scale here, where neutral is set to 7, and that's basically would be water. As you get lower down, 7 down to 0, you get more and more acidic. So we see things like lemon juice and battery acid on the acid side. And then above 7, from 7 to 14, it's basic and becomes a stronger base. So we see things like baking soda, ammonia, and lye, which are all bases. Lye is actually the common name for sodium hydroxide, which is a base that we were using in our chemistry labs as needed when we need to use bases. So, how do we calculate this? Because we love math. This is going to get a little bit tricky, because this is a different type of math than anything we've done before. You guys are probably familiar. I should type this up a little bit better, probably. But, just bear with me here. Okay, so you know what an exponent is. 10 raised to the power of some x. What we're going to be doing, these shortcuts don't look goodness, is trying to get rid of the 10 part of it, because most of our stuff is actually in scientific notation, something times 10 to the x, and we want to break it down just into a normal number. And so what we're going to do is the opposite function. The opposite of 10 raised to some to the x is log. If you have a log of 10 to the x, you get just x. They cancel each other out. Inverse functions. If you look on your calculator, the log is written right above the 10 to the x. Usually it says 10 to the x on the button itself, and then you have to hit second or shift or whatever and make it log instead. And so that's what we're doing. We're canceling out the 10 to the x part of it. And specifically, we're applying this to our hydrogen ion molarity. So, if we want to find the pH, we have hydrogen ion molarity, which is usually written in scientific notation. We take the negative log of that molarity. pH is a positive number. Our scientific notations are very, very small, so usually 10 to the negative x, and I want the negatives to cancel out, which is why it's negative log. So this H plus here in brackets is hydrogen ion molarity, capital M, molarities. What this means, if you have a nice, pretty clean number, if your H plus ion, for example here, is 1.0 times 10 to the negative 6 molar, then your pH is just 6. Because 1.0 times 10, all of that gets canceled out by the log. So negative log of 1.0 times 10 to the negative x is just x. If you don't have a tidy answer like that, then we have to actually plug it into a calculator. You cannot solve these without a calculator, just right off the bat. So if I was doing, if my hydrogen ion molarity is 4.2 times 10 to the negative 6, it's not 1.0 times 10 to the negative 6 anymore, it's 4.2 times 10 to the negative 6. I have to take the negative log of 4.2 times 10 to the negative 6. Make sure this is all in parentheses in your calculator, because otherwise you'll take just the negative log of just the 4.2 and it'll mess you up. And then when I type that all in, I get 5.38. Your pH values will always be positive numbers, and they will always be small, between 0 and 14, because it has to fit on the pH scale. If you're getting like 5,380 or something like that, you're off. You need to recalculate that. And remember, we're always rounding everything to 2 decimal places as well. Okay, we can also do this the other way around. If I give you a pH, you should be able to calculate what the hydrogen ion molarity is going to be, so finding that. All you have to do is take 10 raised to the power of the negative pH. If the pH is a whole number, like here we're given pH is just 3, we're just going to rewrite it in scientific notation. If pH is 3, H plus ion concentration is 1.0 times 10 to the negative third molarity. That's all we have to do. If we have a decimal in our pH, though, you have to use a calculator. You're not allowed to leave decimals in your exponents. That's one of those rules. So if my pH is 6.35, for example, I have to get a calculator, do 10 to the negative 6.35 as the exponent here, just hit equals, and it'll tell me that's 4.5 times 10 to the negative 7th. So this really is just an exercise in using your calculator, and if you've done logs and exponents before, it's pretty easy. It's not a very hard thing to do, really. It's mostly just figuring out which calculator buttons to use and making sure that you put things into parentheses, like up here where I'm taking the negative log of this whole thing. I need that whole thing in parentheses first. So, anyway, don't forget to do the worksheet that goes with this. We are going to be doing calculations in the homework, and I'll see you guys next time.